Hi guys, so I'm Robert Cleeley.
And I'm Tasos Pagastlis.
And this is one of the, hopefully the last video, because we're
Yeah.
spending all morning doing these, that we're going to do. So what we thought would be really useful now is to start thinking about how you could start doing something with factors that we've created.
Yeah.
And Tasos and I have been and added, created a new factor, one which you might have created yourself, which is a general attitude towards the advert based on items 2, 3 and 4.
Yeah.
We had to reverse code some of them. We'll leave that up to you to figure it out. Yeah. And then we thought it'd be fun to see is there a relationship between the purchase intention, the factor that we created through factor means, the attitude
towards the advertisement.
Again, we factor created through factor means, and then some of the demographic data that was captured. Yeah. So to do that, we've used we'll just get the line of code up. We've used the LM function, which is a linear model type of regression. There's other types of regression that you can call.
There are non-linear regressions, logit regressions, probabilistic regressions. There are thousands of types of different regressions. In marketing, 9 out of 10 times it's a linear model of some sort.
And we just wanted to do this just to show you, if you haven't figured it out for yourselves, how comparatively simple it is to actually write the code to operate a regression model.
Yeah, and it is really simple. I mean, doing a regression in SPSS, you probably have to click and point more times than actually just write this single line of code.
Yeah, so let's talk through the code. So we've got this model 3, and you'll probably remember we'd already got several models in our factor analysis. We could call it anything we wanted. We can call it regression. We can well, actually, it might crash because there's probably a function called regression, but we could call it. Let's call it Robert for argument's sake, just to show you. It doesn't matter what you call things. And then we're calling the inbuilt function LM, which is a regression method. And what we're saying here is we want the variable purchase intention. We want to measure how well is it predicted by or correlated to these independent variables.
So if I'm understanding correctly, Robert, so DS purchase, it says find the purchase variable in the D file, in the D object, and that variable is the dependent variable, as we call it, and then we put an ampersand, and then we have the independent variables in our preference order as such.
Yeah, exactly. So the reason we don't have an equals here is because we're not saying it equals this, we're saying it is estimated by
it's estimated,
and then whichever independent variables we think theoretically, or if we're just
relevant
data mining, we think might be relevant. And then that's it.
Okay.
And like with all the other models and the factor analysis we've been conducting, you then need to call it, and you could call it just by typing it in. But that doesn't give you so much information.
The interesting thing is that here, when you call the object, you get only the very basic information. You don't get all the other metrics that can help you interpret how good the model is.
Yeah, so in order to find them, having gone and looked at the documentation, I've seen that for whatever reason the person that's written this function wants you to have to write summary.
Has done it in reverse.
And the summary gives you much more, something which you might be familiar with if you've used SPSS previously.
Yeah, so I think the results are pretty straightforward. For whatever reason, the first results you get are residual results. Residuals in regression are really important. Ideally, you want the residuals to be as small as possible. So the residuals show us how much variance remains unexplained from our model. So you would like the minimum, the maximum to be as close as possible. In our case, it's okay. It's very qualitative to judge the residuals. So when this difference that we're observing here is fairly okay. And then we get the coefficients, which is what we're interested in. So the intercept is a general term, a constant term that we include in all regression models. It represents the error variance, both systematic and random error. So that we can see that the intercept has a particular estimate, which in our case is 3.17. In regression, we always look at the standard error of these estimates. We generally want the standard errors to be small. And then the t-value is used to tell us whether the estimate and therefore the variable is significant or not. In the case of the intercept, we see that the p-value, the probability next to the t-value is over 0.05, which means that the intercept in itself is not significant. So the error that we get in this regression is not really significant. And that makes sense because if we look at the attitude, the estimate is 0.287. And the standard error is 0.07, really small, and then we get a really significant value, a really significant probability. R also puts stars next to the probabilities, which is something very common we see in papers. And that exactly shows how important and how strong the relationship between attitude towards an advertisement and the actual purchase intention is. If we also look at the values for age and sex, we will see that these demographics do not have an effect on purchase intention.
So let me answer your question, Tassos. If you look at the estimate, the coefficient estimates for attitude and sex, gender, they're pretty similar.
Yeah, they
Yet,
are. Yet
one has a really high statistical significance and the other doesn't.
Yeah.
This is something which I think, and I've always found kind of intuitively difficult to get my head around why that is the case. Why can something be significant and something not be significant when they have such similar coefficients?
If you actually see the standard error, you will see that the standard error for attitude is much smaller than the standard error for sex. So that would explain why attitude is significant and sex is not significant. So the sex variable contains in it much more error than the attitude variable. So that's why we see that.
So around that relationship, there's so much more variance.
Yeah, there's so much more variance as such. Yeah. And below the coefficients, we also get all the metrics for the model in total. So we get the residual standard error, which is, as we see, 1.739, and the degrees of freedom. We don't really do anything with these things, we just report them. What we do look at is the multiple R squared and the adjusted R squared. The multiple R squared is the key metric that we report, and what the R squared tell us is the amount of variance explained in the dependent variable by the independent variable. Essentially, in our model, the multiple R squared does represent the amount of variance explained by all the variables in the model. So here, even though sex and age are not significant, they are considered inside the R square. So all these three variables, they explain about 12% of the dependent variable. And the adjusted R square, which is quite lower in our case, is when it says adjusted, it is adjusted regarding distribution assumptions. So it does tell us that the distributions of each variable have certain differences that cause the adjusted R square to be lowered. Ideally, all of our variables would be normally distributed. So if there is a variable in the regression that is not normally distributed, the adjusted R square will always be different to the multiple R squared. But they are different, they're also quite close, so we're not alarmed by that. The F statistic that is reported here with the p-value associated next to it is the F statistic for the whole model. So it tells us that it has 111 degrees of freedom, and the p-value is 0.002, so the whole model is significant. Ideally, if we were moving forward, we would want to rerun the model, taking out age and sex that are not significant, and only keep the significant independent variables in the regression. So when we report a regression, we always report it with significant variables inside of it.
Mm-hmm. And so I guess what you could do, if I'm going off track here, stop me. So we could create Tassos equals LM, and now we still want the same dependent variable.
And
estimated by, and now we're just going to say attitude, spelled correctly, hopefully.
Okay.
So now we can compare Tassos and Robert.
So here we'll look at only the attitude, and here we see that the intercept is also significant. So indeed, attitude explains certain variance, but there is an error term, a part of unexplained variance. We see in multiple R squared that it's 11.5, so all of the other two variables only added 0.004 essentially of explained variance. So most of the explained variance before was from the attitude. And the adjusted R squared is also much better. The F statistic is much higher, and the p-value of the F statistic is also much smaller, so it makes the whole model much more significant.
Let's try doing this. Let's see if we do an ANOVA test, a little bit like we did with the factors previously. See what it tells us. There you go. So it kind of summarises what Tassos has just been talking through.
Yeah, exactly. So it gives us again the differences between the degrees of freedom, between the sum of squares, and it calculates the difference for the sum of squares, and it tells us that this difference is significantly higher than the F criterion. So these two models, the second model is significantly better than the first model.
So hopefully what you started to see, we've started now throughout these videos to use a lot of the same little coding tricks, many of the same functions, and we've actually done some pretty powerful
we've done pretty much
statistical analysis.
All the analysis you will find in an average paper.
And hopefully you can start to unpick some of these ideas and see how to interpret them, as well as how to do them in R, which, as we started out discussing, is a really powerful programming language and is free. And has that real benefit that when you leave the university, you can use R anywhere. It's just freely available. And it lets you do so much more than you could do with some of the proprietary software. So hopefully that's helped give you a good introduction to R, and hopefully you've been able to work through the practice questions. If not, please go on the discussion forums, go on the wikis and participate, and Tassos and I will hopefully give you some feedback.
Contribute as well. We will contribute as well in those forums.